Hi, and welcome to Unit 3.4, Thermodynamics. In this video, we are going to be covering how do we quantify energy transfer during a chemical or physical change. And specifically, it will be a physical change because we're going to be using our heating curves. There is a supplemental video here, so in addition to annotating, you will have to record notes from a supplemental video. All right, you're probably sick of seeing this slide by now. As you know, we're focusing on thermodynamics, and it's one of the two key things that a scientist or a chemist needs to know when studying and making predictions about a chemical reaction. So thermodynamics involves the energy that is either released or gained during a process, and also gives us information about how far a reaction goes. And that is related to Gibbs free energy spontaneity. In this video, we're not going to focus on Gibbs free energy. We're going to go back to our heating curve. So you have a blank heating curve. What I want you to do is I want you to annotate the heating curve that you have with the phases along the blue lines that are shown here. So what are the phases that are there? And including the flat sections, what phases are there. And also I want you to label on the y-axis where would your melting point and boiling points be. So you can pause the video now and annotate that, and then when you press play again, we'll go over what it looks like. All right, so you probably know that the heating curves have the phases solid, liquid, and gas. And on the diagonals, you start at the bottom with solid, the next one is liquid, and the last one's gas. On the horizontal lines, you have an equilibrium situation going on where between the solid and liquid phase, they're in equilibrium with one another as it's melting or freezing. Between the liquid and the gas phase, those two phases are in equilibrium with one another as it's either boiling or condensing. So now that you have the phases labeled, you should also label the melting point and boiling point. So the melting point or freezing point, or the same temperature, occurs here on, is the temperature at this horizontal line. So what you'll have to do is you'll have to scroll over to the y-axis to find what the melting point is, because remember that's the temperature at which something freezes or melts, and the temperature is along the y-axis, so you need to find the value of the y-axis. Boiling point is the same thing, so you would again scroll over to the y-axis at the position on the curve where we're boiling or condensation is occurring, and that value would be the boiling point temperature. Now, a couple of temperatures you should memorize is the normal melting point or freezing point of water, 0 degrees, and the normal boiling point of water or point at which it condenses is 100 degrees. These are things that you're just expected to know because they're so super important, and they actually are the two values that are used to make the Celsius scale. Okay. Now, what we're going to explore in this video is, now that we know what a heating curve looks like, we're now going to explore how we can utilize the heating curve as a tool to help us calculate the total amount of heat absorbed or gained during a phase change. And the reason why that's important is because we go back to our phase change diagram. You'll notice on the x-axis, it's heat added. The amount of heat added depends on where you are in the phase change process. And what do I mean by that? The heat absorbed or gained has different rates depending on if you're dealing with a solid, liquid, or gas. Now, in my heating curve, the slope of a solid, liquid, and gas look about the same, but that's not always true. Like the solid slope can be steeper or it can be less steep than the liquid, and so on. So the slopes are going to determine how much heat is, will help you determine how much heat is absorbed or gained during a process. For the flat portions of the curve, it depends on the length of the curve. So as you can see here, when we're melting this substance, less heat is needed to be absorbed to melt it than it is for you to boil it, because the boiling line has a longer, is longer than the melting line. So in this video, it shows you how to calculate it at those different positions. And what you're going to do is you're going to take notes on which equation do you use at each segment. And there are two examples here. So what equation would you use at this segment, that segment, etc. when you're calculating the heat? The video is linked in the Google assignment, or you can copy this link down. Before you go to the video, I just want to point out to you that these are, there's an additional heating curve in case you need it. And then in addition, there are these example problems that are listed. These are the examples from the video. So you'll do your example and practice work from the video on the next few slides. All right, when we come back together, we'll go over a CFU. Okay, so here are some key ideas that you should have gotten from the practice from the supplemental video. So make sure you've done that first before we just go over these key ideas. If you want to write them down, you can use the extra space after slide 4. But here are some key ideas from this video. So where the temperature changes on the heating curve, that's where you have the diagonal lines, not the flat lines, but the diagonal lines. That's when you're going to use the Q equals MC delta T. And that should make sense because here you have delta T, and that's the portion of the curve where the temperature changes. On the flat portion, the temperature does not change, so you can't use anything with delta T in it. The other thing to note is that the greater the specific heat capacity, the smaller the change in temperature is going to be. And so that means that the greater the C, the smaller the slope. Remember, slope is delta Y over delta X. And since delta T represents our delta Y, since temperature is on the Y-axis, so if slope is delta T over change in heat, then if you have a small heat capacity, you have a smaller change in temperature, as you may remember from the definition of heat capacity. So that means you're going to have a smaller slope. So the main thing to remember is the greater the value of C, the smaller the slope is going to be. There are sometimes questions like that on the AP exam where you're given a heating curve to look at. For example, you're given something like this and you're having to compare the slopes of this segment, let's say, with that segment and see which one, at which point, when it's a solid or a liquid, will it have a greater or smaller heat capacity. Okay, next one. When isothermal, what equation do you use? So that means isothermal means temperature does not change. Iso means same. So when the temperature does not change on the heating curve, that's when you're going to use the heat is equal to the moles times either delta H of fusion or moles times delta H of vaporization. The fusion is where it's melting, and vaporization is when it's boiling or condensing. So those are some key ideas. Again, if you would like, you can record these key ideas. You can pause the video and record them on the extra slides. Okay, so now we have a CFU. For the CFU, it says you have 1 mole sample of water at negative 30 degrees Celsius, and you heat it until you have gaseous water at, I should say, at 140 degrees Celsius. Calculate the Q for the entire process using the following data. So you'll notice you're giving the heat capacity of ice, water, and steam, and that's important because you'll see that the heat capacities are different. And then you're also given delta H of fusion and vaporization. Take careful note of the units. And the other thing I would strongly recommend that you do is I would recommend that you actually draw a heating curve. Don't skip that important step because that is what helps you make sense of what you're doing. So just like it was done in the video, I would draw a heating curve and sort of sketch it out. Mark up your heating curve with things like melting point and boiling point, etc., to really help you understand what you're doing. All right, when you press play again, after you have tried this problem, and I mean really tried this problem, we'll go over what the answer would look like. Okay, so you should have drawn a heating curve like this, and let's see how we can use this information in our drawn heating curve to sort of figure it out. So sketching the heating curve should all pretty much look the same. You'll have 3 diagonals separated by 2 flat lines. The next thing I'm going to do is I'm going to identify the melting point and boiling point of the heating curve, because that's going to help me identify where my initial temperature and final temperatures are. So since it's water, the melting point is at 0 degrees Celsius and boiling at 100. Remember, you have to memorize that for water. Now, I'm starting off at negative 30 degrees Celsius, so that's going to be below 0 degrees Celsius. So I'm going to mark this part off as 30 degrees Celsius. And that should say negative, sorry. There should be a negative there. Then the final temperature is 140, and that's going to be above 100. So I'm going to mark this temperature at this point. So again, I have this to be, again, should be negative 30. I have my initial and I have my final. And then also the other things I have are the melting and boiling points that are in between those. Okay, cool. So how I calculate things depend on the segment. The first segment I'm calculating the heat for is this segment here where temperature is changing. So I know I'm going to be using the Q equals MC delta T. Now I need to keep track of what my phase is. Since it's a solid, I'm going to use the heat capacity of ice, which is the solid form of water. And that's what I'm going to plug in for my C. So I go ahead and plug that in, and then I get this value. I converted it. Initially it was in joules because my specific heat capacity is in joules, but I'm going to convert it to kilojoules. The other thing I had to do was I had to convert the moles of water into mass because the equation is mass times specific heat capacity. I'm given 1 mole of water, and the mass for 1 mole is 18 grams. So I plugged that in as well. So that's another piece that I needed in order to use this equation. All right, the next segment is the melting segment here. So for that segment, I'm going to use moles times delta H fusion. So that's real simple. They gave me the moles. I plugged that in. I have my delta H fusion at 6.01 kilojoules. And so that's real easy. Just it's 6.01 kilojoules of heat was absorbed while I was melting. The next segment is between the melting point and boiling point. And since it's a diagonal, I'm going to be using the Q equals MC delta T. So for this one, I'm using, again, the mass is 18 grams. I'm given 1 mole, but I calculate the mass of water for 1 mole. And then the C, the specific heat capacity, is for water since I'm dealing with liquid. And then this is my change in temperature. So final is 100, and then initial is 0. You always want to do the temperature as final minus initial. So, and if we go back to the purple segment here, the final temperature would be at 0 degrees because that's when that's the last temperature at which I can use this equation, the last segment of the diagonal, and then initial was negative 30. Again, this should be negative 30. Okay, next section is for the boiling segment, and again, for this one I use moles times delta H vaporization, so just go ahead and plug that in. And then the last segment, I'm again using Q equals MC delta T, and the C I'm using is for gas, which here they're writing it as steam. So I go ahead and I plug that in. And I also convert this one to kilojoules. The reason why I'm converting it to kilojoules is because I wanted the Q for the entire process, meaning I wanted total Q. So I need to be able to add everything up. If I left it in joules, I couldn't add them up. So I decided to convert the joules into kilojoules. You could have also converted your kilojoules for the blue and the orange work here. You could have converted the kilojoules into joules if you wanted to. But to keep my numbers small, I converted my joules to kilojoules. Okay, once I have all my values for Q, all I got to do now is just go ahead and add them up. And that's what I have here. So Q total is 0.110 plus 6.01 plus 7.52 plus 40.7 plus 1.45. Add those all up together and I get 55.8 kilojoules. And you may be asking about, like, how did I know where to cut it off? I just use sig figure rules here to figure out where to cut things off. Okay, so that's it for this. You now should know how to utilize the heating curve as a tool to calculate heat absorbed or lost during a phase change. And remember the equations that you use depending on where you are during that phase change process, whether you're heating up a solid or melting a solid or freezing a solid, whether you are cooling down a liquid. So if you go in the opposite direction, you'll be cooling it down, or you're boiling, you're using different equations. So that's why it's helpful to use the heating curve. Hope you found this video helpful. Have a quality day.